Welcome to this worked example on work and energy. So in this problem, we have a 24,000 kilogram aircraft. It's being launched off of an aircraft carrier, and that aircraft carrier launching mechanism utilizes a hydraulic catapult. In the figure, you're seeing a force as is applied over the 90 meter runway. Where it's initially applying a force of 1,240 kilonewtons at the 0 meter location and 205 kilonewtons at the 90 meter launching point of the runway. We're then asked to solve what is the work done by the catapult, and second, what is the speed of the plane at the end of the runway. As a result, first things that we want to go through and look at is exactly what's going on in the problem. And first thing we can observe is the fact that the force itself is a function of the x location. If we go and we look at this, we can observe that we have a starting location of 1240. That is when x is equal to 0. And we can observe that it is decreasing at a linear rate, so we can observe the fact that we can take our final position minus our initial position and observe that we have 205 minus the 1240, and that is over our final position minus our initial position, so 90 minus 0. This provides us with the, so to speak, slope that we're observing for the decreasing amount of force that's observed, and this is over the x distance that we have. If we solve this through, we can rearrange into a equational form that will show us that we obtain a value of negative 11.5 multiplied by x plus this 1240, so that we get the initial value that we desire. And the units of that are in kilonewtons. Now this is important because what we can observe is the definition of work, where work is defined as being the integrated value of the force over the distance, and the distance is 0 to 90, and the force equation itself is 11.5 times x plus the 1240. If we go through with this integration, we observe that we get 1/2 of the negative 11.5x now squared plus 1240 multiplied by x. And this equation is now solved from 0 to 90. This provides us with, when we solve, an overall work of 65,025 kilonewton times meters. So this is the work that we have present. Now, if we want to continue with this concept, what we can observe now is the idea that this is the work that is completed. So that is the work done by the catapult. So that completes our first question in the problem statement. The second question, where we want to know what is the speed at the end of the runway. Since we're utilizing a hydraulic catapult methodology, what we can observe is the fact that, again, we can return to the definitions of work being equal to a change in energy. Now, again, we've separated external work from potential energies where we have things such as springs or gravity, therefore changes in height, and now also kinetic energy. So we can go with the definition or equation format in which the work done on a system is equal to the change in kinetic energy plus a change in the potential energies that we defined due to springs or height changes. Since we're talking about an aircraft carrier and we're assuming the aircraft carrier is at a proper level position, we're going to assume that the height of the plane does not change as it's being catapulted off the runway. So as a result, our potential energy is equal to 0. If we now look at the work and we convert this to Newton meters to make certain that we convert ourselves down to newtons and base unit forms, we have that 65.025 times 10 to the 6th Newton meters is equal to 1/2. Our mass is given to us as 24,000 kilograms multiplied by the velocity squared. Now this again is our final velocity. We're starting from rest, so we're allowing ourselves to assume that with it being at rest, initially we don't have to worry about any change really in kinetic energy, the change in kinetic energy is simply finding the magnitude of our final kinetic energy, therefore using our final velocity. If we now solve this, we find that the final velocity of the plane will be approximately 73.6 meters per second. So in this problem, we've allowed ourselves to utilize the system to find out what is the external work being applied due to a linear force. So we've taken an expression for force. Again, in this case, the force was applied as linear force, but certainly as long as you're able to find the force as a function of x, we can then integrate that with respect to x to find what the work is for the system. And then we took that work and returned to our basic definition that work is the change in energy. In this, we were able to observe there were no changes of potential energy as there were no springs or gravity effects due to no height change. And so our work is defined purely as the change in kinetic energy. Since it was starting from rest, our work done is simply equivalent to the kinetic energy that the plane would have at the end, allowing us to find the final velocity.